we want to end chapter 5 talking about a little bit of context about all this material and answering a very important question. Why do we care about thermodynamics? And we started off by talking about heat, and a lot of the early ideas behind why people came up with any of these ideas was to effectively apply and use heat. You want to cool something down to a certain temperature. You're going to put it in water. How much water do you use? What temperature is that water going to become? Right? Those sorts of things, right? How much that allows you to do heating and cooling. From a chemistry perspective, you're going to burn heating oil in the winter. How much heating oil do you need to burn if you want to maintain a temperature in your house? Your thermostat does these calculations in order to figure these things out, right? How much should it burn? However, if you have a furnace where you're burning it, what rate are you burning it at in order to kind of maintain the temperature or maintain the heat flow that you're looking for? In a chemical context, kind of in a laboratory context, we also have learned that we can move beyond just applying heat, and we can start to make predictions about experiments without having to do those experiments. We can use things like Hess's law, right? Other people have figured out how hot or cold reactions are going to get, and we can determine it for related reactions that we're interested in studying. Formation enthalpies. You can just determine delta H for just about any reaction that exists using that tabulated information. A lot of people did a lot of very tedious experiments to come up with useful tools that we can use and apply to any reaction that we want. And really the end goal of thermochemistry is not only describing reaction, but really predicting, will a reaction even happen? Now we can predict, will the reaction be exothermic or endothermic? We want a slightly different answer of, will this reaction even happen? If you mix these two reactants together, will they make product? So let's look at kind of a context of that. Different metals that you have, say sodium, magnesium, iron, lead, and copper. If you put them into acid, you get different tendencies to react. So sodium reacts so aggressively it lights on fire. Magnesium, lots of bubbles. Iron, some bubbles. Lead, barely any bubbles. Copper, nothing happens. Copper does not react with acid. So why not? Why is there this different tendency? Why does copper not do it at all? And why does sodium really aggressively react? Where I'd say magnesium, iron, lead, you have kind of this range. What's going on there? So the reaction that doesn't happen is our acid, remember H plus for acid, plus copper. You'd form that into hydrogen and make copper. This is a redox reaction. So the delta H in that case is quite positive. It's 64 kilojoules per mole. Magnesium reacts pretty strongly with an acid, and its delta H is negative 476. And so we can see it's exothermic. And if we think about this idea, exothermic means energy comes out of the molecules. It comes out of those atoms and molecules. And so the atoms in the reactants are at a higher energy position. They have more kind of internal thermal energy, and then they release that to the surroundings. So overall, those molecules become more stable by undergoing the reaction. So we can see that the real reason why this copper reaction, why acid doesn't react with copper, is that it is an unfavorable energetic change. Copper, as a solid, has a relatively low energy, whereas copper as an ion has a relatively higher energy. So it does not want to form ions because losing those electrons has an energetic cost. There is some sort of cost to losing those electrons, whereas magnesium really doesn't care. It is more stable for those electrons to move over to the hydrogen atoms and for the magnesium to be left as a cation. And so what we can start to see is that things that are more exothermic are more likely to happen. They are not guaranteed to happen. Plenty of endothermic reactions happen, but the more exothermic a reaction is, the more likely it is to occur. It's not the whole thing though. Enthalpy isn't it. If we look at, say, dissolving. So we talked about salts that were insoluble. So if we had an insoluble salt, for example, silver chloride, you put solid silver chloride in water, it just does not separate out into ions. You do not dissolve. If you put sodium chloride into water, it very much dissolves out into the separate ions. Both of those are endothermic processes. That's because when you're in both cases, you're breaking ionic bonds. And so those breaking ionic bonds, always corresponds to putting in some energy. But there is something else going on here besides enthalpy. We know that based on the enthalpy considerations, we can understand the pattern, but it doesn't let us predict everything. We can see that silver chloride dissolving is much more endothermic. Sodium chloride dissolving is barely endothermic, whereas silver chloride is very, very endothermic if that were to happen. And that's why it doesn't happen. Basically, you have a really strong bond in the silver chloride solid, and you don't want to break that in order to dissolve. Whereas sodium chloride isn't that strong of a bond, so it'll break apart, no big deal, and dissolve out separately. So we can use it to understand patterns of reactivity. More exothermic means more reacting. If we also look at our table of enthalpies of formation, if you ever look at one of these, enthalpies of formation are almost always negative. And that is because you're taking elements and turning them into compounds, which is all about forming bonds. And we said that forming bonds tends to be stable. The reason why atoms do chemistry is to become more stable, right? To release energy, to go to a lower energy state. And so the formation of bonds is in general exothermic. And so enthalpies of formation are almost always negative. The only time when they're positive is because there's other molecules that those elements can form that are more stable. And so atoms tend to form compounds. And the reason they tend to form compounds is because of energy. And this is getting at the reason of we can understand why and how chemistry happens by understanding the energetic basis of it. So we know in general the reason why chemistry happens is because it's more favorable for atoms to form bonds than to be isolated elements. And so, we can follow this trend further and predict particular reactions, not just say going from elements to molecules, but from one molecule to a different molecule. Is that going to happen? What is the energetic driving force for that to happen? Unfortunately, got to come back for Gen Chem 2 if you want to learn the answer to the using the other two columns on this chart to figure those things out. There you go. Chapter 5. Started, just basic ideas about what energy is, kind of building up to defining enthalpy and applying it to chemical reactions, the importance of enthalpy within chemical reactions, and then all of the ways that we can come up with values for the change in enthalpy for a reaction using the fact that enthalpy is a state function. Those Hess's law ideas, formation enthalpies, really powerful tools that help us to come up with values for delta H, which we've previously seen as important. Okay, no participation questions on this video. 618 is what we're looking for. This is, importantly, the end of chapter 5, but not the end of this set of videos. We're going to start do a little bit on chapter 6 here. I'll see you in those videos.